Okay, so I did a sort of informal survey of people, asking them if they know what differential image motion monitors do. And I'm happy to report that I got blank looks from 8 different people. So that made me feel good, like I'm actually presenting something sort of original here. The last 4 times I presented on photometry of various objects, stars and asteroids. And this is going to be a little bit different. So I got hired at Lowell Observatory to operate that telescope. That's a 42-inch Hall telescope at Anderson Mesa, mostly observing asteroids with Brian Skiff, who didn't want to stay up till dawn any longer, and I do. And so I did that for 3 or 4 months, and then switched gears in fall and autumn of last year and started doing seeing measurements. So if you go to any observatory, any modern observatory, there has been extensive site testing done. And of course, one of the big factors is clear skies, number of clear nights, and you can't be going to Chile for that. Then Arizona is good in the continental United States, and you'd like it to have dark skies. Well, what you really want, if you're going to put a 4-meter telescope, and we just heard a talk about speckle to resolve double stars, you want good seeing conditions. Really important. And everybody in here knows that, but that's, can't emphasize that enough. Okay, so the purpose of the thing was they got funds to install a 1-meter class telescope at Anderson Mesa in addition to what's already there. And they have 2 domes that are about a 1/4 mile apart. And this is common to most professional observatories, that both of those domes have obsolete telescopes. And one of them is called Lonios. It did asteroid discoveries back in the 90s, a little bit into 2000s. And then the other is a 31-inch that just got shut down. And I'll describe those a little bit more. So we know that seeing is affected by 3 things. It's the what's up 10,000 feet and higher. It's what the air aloft is doing. If you're under the jet stream, there's not much you can do about that. That's just going to vary from night to night. The telescope enclosure itself, of course, affects the seeing, and they really see that with the 42-inch. And then there's a local terrain, and you can do something about that by setting up at the optimal spot. And that's what these site surveys are about. So what we did is we set up a small scope, a Celestron 14, and you can do that portably. And I'll show you the list of equipment is really simple, and it's an alternative way to measure the seeing conditions. So we did that at Anderson Mesa, which I'll show you where that's located, and then moved it down to Lowell's flagship telescope, the 4.3-meter Lowell Discovery Telescope, and we're currently doing that. Okay, so what I'm going to describe is just how does DIM work and how you acquire the data and everything, talk about the observing sites a little bit, and what we got for results. So this illustration that I pulled off the web, nice illustration that shows you have this turbulent air and you have seeing cells, moving around overhead. So what you do is you cut a mask, cut 2 circular holes in a mask. In this case, for 14-inch, cut 2 4-inch diameter holes as far apart as possible, and put an optical wedge in one of those holes, and that's going to deflect the light, in this case by 25 arc seconds. So you're going to have 2 sharply focused star images at your focal plane, and they're going to move around relative to each other. So what you'll end up doing is recording about 1,000 frames on a modern, simple planetary camera that you buy for $300 or $400. And in those 1,000 frames, they write a script that's going to measure the distance between the centroids of those 2 star images. And then with some pretty simple math, you can translate that into what the full width half max seeing is. So here's that wedge on the left, and then on the right is just an open hole. So your equipment, as I said, it's real simple. Just best to have a catadioptric telescope like you see 14. You have this mask with the wedge, planetary camera, and then a laptop with some capture software with fire capture or whatever. That's all we use. And of course, as you go on in the project, you keep complicating it by adding a finder scope and a guider and a focuser, all that stuff. But what you really need is just this. So up in the upper right is kind of animation of what you see in the capture software. So just some frames running on an animated GIF show you that it doesn't matter if you have bad tracking. It doesn't matter if the wind's blowing, because that's moving the two star images in unison. All you care about is the difference, the distance between the two star images. How are those centroids moving relative to each other? So what we would do is we record 1,000 frames. We started with a 20 millisecond shutter speed, and then we do this every 5 minutes. So what you end up with is, oops, sorry about that. I'm not going to run the laser pointer. Okay, the table that you see that has frame number, that would go up to 1,000 in each case. And then you'd have a kind of a table generated that gives you the distance between the two image centroids, the two star image centroids. And the final output of all this is that versus universal time on that night, you would have the scene. And that's just a cartoon of what that's going to look like. So I'll show some of those plots. A little bit about the site. Here's, doing it again. So in top left is the inset, just shows the whole state of Arizona. A lot of people here have been to Flagstaff. And if you're in this room and you've been to Flagstaff, you've probably gone to Mars Hill. That's the main Lowell Observatory site, which is becoming more and more of a tourist destination. They're building a gigantic visitor center there that's going up, a new visitor center. Not a lot of science goes on Mars Hill. They have a deck observatory and a lot of public outreach. So for that, you go down the road, you're 9 air miles from Flagstaff is Anderson Mesa. Because Flagstaff has the best lighting ordinance in the country, thanks only to Chris Luganbuehl, you have a sky that's only 0.3 of a magnitude above the natural sky brightness. It's really impressive. And you go farther down the road past Lake Mary or past Mormon Lake, and you get to the LDT site. That's about an hour away from Flagstaff instead of 20 minutes. And so we've done, that's where the 4.3 meter telescope is. So one of the perks of working at Lowell is they let me fly my drone and run around and take all these pictures. So here's a picture heading, looking to the northwest toward the San Francisco peaks. The Lonios is at the lower left. At the upper right's the 31-inch. I worked at the 42-inch, which is just right of center. And at center is a 72-inch Perkins telescope, which is now owned and run by Boston University. Out of the frame to the right is the prototype, Navy prototype optical interferometer, which is by the end of this year, Lowell will not be involved in. It's a little news flash there. Okay, so a closer view of the two observatories, 31-inch on the right with a Astrophysics 1200 mount. I got to run that most of the time, and that's fortunate because you don't want to run the one on the left with the original fork mount. But one thing about the one on the left, you can just see the edge of the dome is kind of corrugated steel or corrugated metal. And the one on the right is this brick thing structure. And so if there's, in science, you're trying to make an objective measurement, but everybody's rooting for the one on the left, which is also farther back on the campus, to win the seeing contest between these two, because the observatory won't have to be completely demolished and redone. The observatory is not going to contribute as much to the seeing because it's not retaining all this heat all day. So here's a real version of that cartoon plot I showed earlier. And Julian date down on the bottom. This is about, probably 6 hours, 4/10 of a day. Yeah, 6 or 7 hours, most of a night of seeing. We did this in October and November at Anderson Mesa. Then the red is showing a 31-inch dome. Green is showing the Lonios. This kind of stuff happened once in a while where you would have some stray points that we're not going to be able to explain all of that, but as we've been discussing, keep all of the data. And so we have this for a large number of nights. We have these types of plots that overlay the two sites. And sure, you'd like to do 18 months of this, you know, which is what they did at the original LDT site survey. They did a year and a half. But even just doing a month and a half, a couple months, and what we're trying to do is just isolate if the local terrain is affecting the seeing at one site worse than the other. And I think just doing a couple months as we did was enough. And so if you ever look at site surveys, they always show a histogram of what the seeing looked like, and the important number of in those 28 nights at the upper right is the median seeing. And you want to know those other numbers as well. And at the two sites, it's 1 to 1.1 arc seconds. And this was kind of a pleasant surprise that it's as good as it is, because nobody had done this type of survey or measured outside of the dome what the seeing is. Because I know from the 42-inch operating at that the seeing was always 2 or 2.5 arc seconds at the camera. And so all of that that degradation has to be happening between the ambient air. And we even have direct comparison on the same night. So some of these that shows what's happening between the ambient air and what's getting to the telescope. So it's kind of a nice result. And we discussed this, and this is going to be a slow moving thing, but they will pursue the Lonios dome. The other advantage of the Lonios dome is that you're farther away from the entrance to Anderson Mesa, which is just out in the National Forest. So the partiers on Saturday night are a quarter mile farther away. That's a good thing too. Okay, what I did on one night was at Anderson Mesa. One of the observers, who will remain nameless, doesn't like to work weekends as an observational astronomer. So, and I just want to work every night. So he didn't show up. So there's no point in doing just the conventional seeing measurement when there's nothing to compare it to. So what I did was pointed the telescope at nearest the zenith as I could. I'd pick programmed stars for every hour and then work my way down to 10 degrees, which is about 6 air masses. And let's see how much the seeing degrades between the zenith and near the horizon. And this kind of, for this room, it's kind of a trivial result. But for a lot of amateur astronomers who I see at star parties pointing at the Ring Nebula when it's 20 degrees above the horizon, I try not to lecture them, but yeah, don't do that, because you're losing in contrast, you're losing in sky brightness, really losing in seeing. So here's what we ended up with. Rather than air mass at the bottom, I put altitude in red, 90 degrees, 30 and 20 degrees, and then a bunch of pretty widely scattered data points that I got throughout that night, which is a really stable night. And so we have nearly a half arc second at times down near the zenith. And probably the easiest way to express the result is if you go to 30 degrees, you're about twice as bad for the seeing as you are. There's actually a turbulence model called Magra, if I'm pronouncing that wrong, that's in red. And then there's my little Hopi XL curve fit, logarithmic curve fit, which has a decent correlation at least. So it kind of shows how the seeing falls off. And it was just an extracurricular thing that I did. So from that, conclusions are that we got about 1 arc second at both sites, as I mentioned. We have a bunch of weather data, and I'm not going to get into that, and nobody really has yet. They've collected at both sites. We had Davis weather stations right next to the domes. And so we know the direction of the wind, we know all that stuff. But without even having that weather data, what I can tell you is that when you have the prevailing southwest wind that we have in Arizona, that's always good. It doesn't matter if it's 5 miles an hour or 20 miles an hour. If it's southwest or west, even a little bit south, that's most of the time. And we're having this arc second seeing on nights after a trough has passed. Then you have the north or northeast wind on the backside of the trough. It's always 2 or 3 arc seconds, and sometimes way worse when it's a strong trough has gone through. So there's also this myth, and again, I'm speaking to a pretty advanced room, that you have to go to Florida to have good seeing, or you have to be on the ocean on the West Coast where it's laminar air. But it's a myth, because here we are in northern Arizona. You just have to be above the local terrain. And so one of my observations from a lot of nights or at dawn coming down from both Anderson Mesa and from the LDT. Anderson Mesa is 400 feet above the terrain. The LDT is 150 feet above the flats. And these last few nights that I was coming down from LDT, 60 degrees and a little breezy. You get down to the plains, it's 45 degrees. And I've observed a lot from the meadows as a visual observer. It's always bad seeing. So it's just a matter of being up on that hill. Best case is that hill has a steep cliff facing the southwest. If you go to Apache Point in New Mexico, same thing. They've built out over that hill to the southwest. So it's interesting, just the whole study and the fact that we can measure that with these small portable scopes. Okay, and now a couple more drone photos. They actually let me fly my drone with the dome shutters open to the 4 meter. I said, I'm not going to fly over the top of it. And so did a little bit of that. We have encircled or in the square in red is our little roll off, which is this kind of decrepit thing that rolls off of the entire telescope and protects it somewhat, although snow gets into it, of course. And that's where we set up relative to their 4 meter telescope. We began in January in the coldest time of year. I'm a desert rat, and anything below 40 degrees is cold, and now I have to go out in 10-degree cold. One thing we did differently is we got second guessed after the Anderson Mesa study by Tom Bida at Lowell, who did the survey, the seeing survey 20 years ago. He's right, we should have done more with shutter speed. So we were doing 20 milliseconds. He said, let's vary it all the way down to 2 and 5 and 10 and see how that affects the results. And as you record with shorter shutter speeds, to an extent, you're going to see worse seeing, and then it's going to kind of level off. So we did some of that. We had the intention of comparing the CMOS camera method with what they did 20 years ago. They dredged up the old DOS machine or whatever it is, 286, and then the old CCD camera where they did strip scan measurements and got a little ways with that, but no results worth talking about yet. So here's what we got. In this case, this histogram has 2 color bars. The black ones represent 20 milliseconds and the green ones are 10. The green are going to be a little bit worse. As I was saying, as you get to shorter shutter speeds, we've done 5 since then, and it doesn't keep getting worse. So this just kind of tells you something about the frequency of the movement of those seeing cells that are over your telescope. And what we got, again, the important numbers on here are 0.96 and 0.84 arc seconds for the median seeing. And probably the more correct number is 10 milliseconds, or at least the one that correlates with legacy seeing measurements that have been made. So we expected that the median seeing at the camera when they measure it at the LDT is 0.9 arc seconds, which is great. And I've been there when there's a remote observer and a telescope operator and me, and that's just only 3 people. And a remote person is always asking a telescope operator, what's the seeing? What's the seeing? And they're really excited when a low number comes up. So no matter what you're doing, it's the most important thing. And so that's it's a very good site and a state-of-the-art telescope, and I can't stop speaking glowingly about how well it's done. And like so many of these things, you know, there's a team of people, but there's one person, Stephen Levine, up there, the commissioning scientist, who is much of the reason it's as good as it is, because he's so thorough. All right, and I think I just had a couple more slides. Yeah, so. And they let me run around and take pictures with my SLR, so I feel compelled to throw some of those in here as well. So at the LDT, we had 0.96, depending on your shutter speed, but we're getting 0.8 to 0.9 arc seconds seeing. What hasn't been done yet, and part of the purpose of this was to compare the ambient seeing to what's happening at the telescope. Thanks, Rachel. And so we'll be able to do that, but that's somebody else's job at this point. So we're going to use 10 millisecond shutter speed. We're still doing some of that, fucks around with varying the shutter speed to see how that affects things. And one of the other purposes, which I'm just going to give a hand waving explanation of it, is with this type of data and being able to change the shutter speed this way and model the frequency, if you will, of this seeing, if they pursue adaptive optics with this telescope, then that's going to kind of guide them in that effort. So to have a semi-permanent seeing monitor like this, that isn't the 4-meter telescope, is going to be helpful as well. Right now they have active optics, which, as you know, that just allows you with the pistons to keep the same form as you go to different altitudes with an L telescope. But someday maybe they'll add adaptive optics, and that's the kind of thing that just costs money, which they have. So that's maybe what will end up happening with this, but there's no sign that this is going to end anytime soon because it's working successfully. Okay, and then I have to show this picture because this is one of the coolest things you can buy for $30. I know nobody on here is interested in this, but I'm going to talk about it anyway. You can buy it's called a lens ball. And so I love SLR night photography. So you set that on a little mount and you focus on the lens ball with your macro or whatever, and then the star colors are in the background, all defocused. And the best mounting hardware I found was 4 Peaks tilt lifter AL. That's a good mounting hardware for the ball. Okay, so if anybody has any questions, I'll try to bluff my way through it. Answers.
Have you seen any data where you take the telescope and take a, say, 3-minute time exposure series of exposures and measure the full width of the real image versus the seeing monitor?
We'll have a lot of that because that's actually about a typical exposure for the LDT for the 4-meter. So we have a lot of that already, where you can just do our conventional measurement of the point spread function of the full width half max. What we haven't done, and that would actually be appropriate, is another C14 that's just taking conventional images right next to it to kind of calibrate it and show that the method works. But what we'll have to do is take that at face value. This is not there's nothing new or racy about this. It's been around since the 1980s, I think the early 80s, and used practically. I think the first time was for the wind telescope at Kitt Peak, like in the late 80s when they were doing the site survey for it. So it's a reliable technique. The only thing that's still bothering me about this is the shutter speed changing the results as much as it does. So yeah, ideally you would set up one right next to it and say, yep, it's given the same result as the full width half max, and we're kind of doing an apples to oranges because one's inside the dome with the 4-meter telescope.
We have 2 online. I'll go with the first. Going good. Good. Okay. The first is from Mark Cooper, and I'll just read it because I'm not sure I completely understand it. And I'll leave it up to you. Poor man's DIMM, no optical wedge, question mark. Use Hartmann mask plus slightly out of focus. Tocovinin doesn't like, but seems to work okay to me.
So it sounds like what he's saying is if you don't have an optical wedge handy, that is another method. I talked here, well, actually online 2 years ago about attempting to do photometry of Betelgeuse, and we had 2 holes that were just trying to stop down the aperture, and you would end up with defocused discs. So they don't come out perfectly in focus is one of the problems of not having an optical mask, of using the Hartmann mask. But if you don't have that, it would be a valid thing. You want to be able to find the centroid, and I don't know how much more difficult that gets if it's out of focus. So.
And I got another one while that was being answered, but yeah. So the next one is from Tom Smith, who I will say he answered yes, he knows what these are. He says the optical wedge you use, what is the divination angle on the scope mask?
I have no idea. That I was handed an optical edge and a fixture that was already pre-made by Stephen Levine, and he said, "Here, use this." And I can tell you that it deflects the starlight with, I don't know what the variable 3,900 millimeters of focal length of a C14. So it deflects it such that the centroids are separated by 25 arc seconds. But I couldn't tell you anything about the optics of the optical edge, other than the fact that it ices over during the winter every time.
Tom, I think it was the 42-inch on Anderson Mesa. You mentioned, the native seeing was 1.1 arc seconds,
Yeah,
but in the dome at the telescope was 2-ish or worse.
yeah.
What can you say about what's happening right at the scope, or maybe what they could have or should
I'll
have
go
done?
back to this dome is for somebody who still loves the aesthetic side of astronomy. I'll go to the title slide here, and it shows me standing out. Has this beautiful catwalk out here. It's an old school 1970 dome, but what you're seeing the dome being constructed of, or at least the walls of the enclosure, are this brick. It doesn't, amazingly, it still doesn't have air conditioning in it. So you're trying to release that heat, but I don't think it ever really equilibrates all night. So I think it's always a problem of dome seeing. And we know now that domes are not what you make professional observatories, and you make them out of more irregular kind of these, what you would call that structure with the angled roofs, but and you make them very ventilated. And the ventilation of the dome, in this case, consists of that door that you walk out of to get on the catwalk and the slit. And it's not enough. And so I think that's entirely what's causing that degradation in seeing. And it doesn't really get better by the morning and doesn't improve that much.
Quick question on the aperture. So you're talking about a C14. What if you built one out of a C6?
You could, but now and maybe it wouldn't matter that much. Now you're going to have to put those holes, what is it, 2 inches apart or 2 inches diameter. And I can't speak to that. I can relay that question that I would think you'd want those holes to have some nominal separation such that they're seeing different columns of air.
Yeah.
And as they get closer and closer, I would not think that would be advisable for measuring seeing between two apertures that might be in the same column.
Okay.
So, right.
Thank you.
We had one more online here. I think you started to answer this kind of, but it says, I think you said the seeing was significantly worse in the domes. How do you explain that? The domes are elevated above the ground, which should be an advantage. I think he's asking about dome, maybe explain dome seeing.
That's the same thing. So I would add that one of the things that we did do at the very beginning, and I didn't really show that, was we were both, just to make sure the systems both worked, we were both set up at the Lonios dome. One of us, me, outside on a little recently poured cement platform, and then another observer up in the dome where it is and elevated. And we got about the same result, which was inside and outside the dome. And we think that elevation helped, and the fact that it's not made of this thick, concrete, this block construction kind of thing helped as well. I think a lot of it is just heat retention from everything that's below the observing floor of the 42-inch, and that's just constantly radiating all night. Oh, I think we got one more back under this. Oh, it's Tom K.
You are an astronomer, right?
I'm now, as of a year ago, I'm a semi-professional astronomer.
So, somewhat anecdotally, they talk about the seeing cells in the atmosphere as being roughly 10 to 12 inches across, right? I don't know if it's true, but this is what we've heard. I'm sure you've heard that story. We also hear the idea that it's like a 10-inch telescope is always going to outperform a 40-inch because of that fact you're looking through one seeing blob, not 10 of them across. Is that a factor, do you think, in terms of using a 14? Because
Yes.
theoretically, you're looking through a smaller blob versus the 40-inch that's looking through a whole wide swath of them.
That could be, but you bothered me by one thing about because I've done so much visual observing in my life. I've more than probably anybody here. I mean, I'm not bragging. That was my background. And I observed planets ad nauseum, and the larger aperture always outperforms the smaller aperture, no matter what comparison you make. But yeah, I know you notice the seeing more, but you always see more with the larger aperture. But I think what you're asking is, yeah, because you're seeing more individual seeing cells
Seeing a
under
bigger chunk of the
42
waves,
inches.
yeah. You're seeing multiple waves versus one, theoretically one lump in the ocean.
But the thing that would refute that is that the 4.3 meter is getting almost the same seeing as we're getting, we think that's the result, because we're getting 0.9 arc second median seeing at the focus of the camera of the 4.3 meter Lowell Discovery Telescope. And then we're measuring something similar that outdoors.
Okay.
So,
right,
so
that's good.
it has to be something where you're mucking with the environment by adding this building that's in the way and not ventilating it
Okay,
properly.
that's actually very good. I was always
Yeah.
curious about that.
Yeah,
Thanks.
I'm glad I recovered from that answer. I was flailing around on.
Okay, I think that's the end of the questions. Thank you so much, Tom.